Okay, let's get going. So once again, we missed another day, but I think we'll be okay as far as catching up. At the end of, well, this lecture is actually going to be broken into two parts because we're kind of going to squash two lectures together. It'll work out just fine, I think. And what we're going to do is we're going to start with these things called sets and cues. In the middle of that, when we get to the end of this part of the lecture, I will make some comments about the current homework assignment, which showed up on I think I posted it Sunday, but it's not due until next Sunday, like a week from this Sunday. So you've got a little extra time. For what it's worth, those of and most of you I'm not talking to, but for those of you who were really down to the last minute because you had lots and lots of bugs in the last assignment, please don't start this one late. I'll say it every time, and then I've yelled at probably 5 or 6 people who've asked me for extensions, and I've said no. Said you don't deserve an extension. You just told me you started it on Wednesday. Sorry, no extension. And then hand in what you've got. So please start it early. Okay? Some people I know have already either done the whole thing or almost done with it. So it's not that hard to do this assignment, right? There are still some memory leak issues and that sort of thing, but again, you have to learn that stuff. So I'll continue to talk a little bit more about that. Anything else before we get going? Okay, so here's what we're going to do today. First part, comments on homework 2 and lab 1. We're still in the middle of grading homework 2, but I've got some comments on that. Then we'll do a quick Unix tip of the day. Again, I'm not going to show you the Eclipse tip of the day just because of time. I will show you one in the second half, but this is more debugger stuff. So if you do want to learn how to use the Eclipse debugger, come see me, or I'll show you how to use GDB. Okay? Hey guys. Shh. Thank you. So we're gonna talk about a little bit about that. Then we're gonna go into these things called sets and cues. Okay? And cues are what sets and cues are what the assignment is on. And cues are the ones that you actually have to build, and they're a little bit tricky. Okay, as some of you guys emailed me the last couple days who started it said, I don't really get what's going on here. That's because cues are a bit trickier than they might seem at first. Okay, all right. First things first. Let's do the Unix tip of the day. So this is there's two. Did I already show you Control R completion? Do you guys remember that? I don't think I did. So if you have a bunch of files in your folder, right? In this case, I have a couple that are called hello something something something. If I start to type, let's say I type LSHE and then type tab, it will fill in as much as it can until it can't fill in anymore because there's things that are the same. So I typed HE and then I hit the tab button and it said, oh, you want to get to hello? Okay, there's some things called hello in there. There's not anything called help. It happens to go all the way to hello. If I hit tab again or twice in a row, it will tell me all the things that start with hello. And then I can say, oh, I really want to do hello world. So if I start to type W and then tab, it'll fill that in, right? So it's actually a nice way to walk through a directory structure without typing everything. That's actually kind of cool, right? And then there happen to be a couple here. And then if I do C and then tab, it'll fill in. And then once it puts a space, it says that's all. This is the only thing that meets that criteria. Okay? If you happen to be on the homework server and you're want to go into the folder directories that we have, watch this. CD/comp, and I'll hit tab, 15/p, and I hit tab, and it fills in the whole public_HTML, just like that, right? And then let's say assignments, AS tab, it fills in assignments. See how much faster this is to get through the directory? And then files, or actually homework, and it happens to be a couple in there, homework 0, 1, 2, and 3. Homework 3/F will give me files, etc. And then boom, I'm right there. So it's a really quick way to speed up some of your directory operations when you're in Unix. Okay? Let's see, what was the other one that I had here? Oh, Control R completion is a cool one too. Control R completion says, hey, if I typed a command recently and I click Control R, it says reverse I search. And then if I start typing something like ls space, oh, it'll tell me what I've actually done recently. So I happen to type the command sudo ls-l blah blah blah, and that's it. And if I keep hitting Control R, it will go back, keep going back farther and tell me all the different commands that I've used ls for. So it's actually kind of a neat way to go back in your history for what you've typed on the command line. right? So I use that all the time these days, once I learned about that. And I've been doing Unix for longer than you guys have been alive. And I just found out about this like 2 years ago. So it's one of those things, you learn new things on Unix all day, every day, right? OK, questions on that? All right, Control-R completion. Kind of neat, and tab completion. OK, comments on homework 2. So to those of you who I actually talked to in the lab or in office hours, I saw a lot of people using the has card method in their linked list methods. And we're actually going to take points off if you did this. If you used has card or cards in hand in any of your methods, guess what? You don't need to. OK, and here's why. So remember, homework assignment 2 is about linked lists. OK, and linked lists, right? We all know what linked lists are at this point. Head, and then all the way through, right? If you're trying to do anything with a linked list, is there a reason, besides needing to know how many cards there are in that linked list, is there any other reason to call cards in hand? Like a lot of people said, OK, for instance, for insert at index, right? In that function, the first thing some people did was they said, let's see, they said like if index is greater than cards in hand, like that, do crash somehow, or return a dummy card or something. Well, what does cards in hand have to do for a linked list? It has to walk through the entire list. So you've got to go through this one, and this one, and this one. And asymptotically, what kind of behavior is that? Linear behavior. So right off the bat, you've got linear behavior going through that list to somehow do this, right? That's not efficient. There is no reason to do that, especially since I told you that your program could crash. We will never ask you if index is greater than cards in hand. I'll never even ask you that. Like I even promised that to you. Right? So bad news if you did something like that, right? How about has card, right? If you're doing remove card, remove C, right? In your remove C function, a lot of people say if has card, well, I guess it would be your list, but if has card, no, I guess it would be like this. Has card C, no, if not has card C, like return either a dummy card or I guess it was a dummy card or something like that. What does has card have to do? Iterate through the whole list, right? It has to go through the whole thing. Don't do that. All you need to do is forget about this, right? Just go through the list, and as you're walking through, see if it has the card, right? So you're not really saving anything in the big picture by doing these two functions, right? So I was a little sad that some of you guys thought you had to do that. Now, for the future, you've got to know what all the functions you're using are doing so that you can not do all these non-efficient types of things. Like, don't walk through the whole list. Even worse were the people who used, what was it? They used one of these to actually find, if it was insert at tail, they used has cards to figure out how many cards they'd have to walk through to get to the tail. And then they'd go walk through that many cards. That's completely inefficient, right? All you need to do is walk through the number of cards until you hit the last card is null, right? So keep those things in mind, OK? In the future, we want to be more efficient, OK? All right. A couple other things from homework 2. A lot of people did things like, for I is less than index -1. And you had no comments about the -1 part, right? We'll take points off for that. If there's no comment about why you're doing a for index something to something -1, I have no idea why you're using -1. Some people put -2, which is even more bizarre. But if you're walking through a list and you happen to say something like, well, if you're going up to some index value, you better put a comment like, go all the way to the end of the list, or go to the one before the end, or something like that. That's a perfect place for a comment. Okay? You'll see this when you get the results back. We actually looked at that. Okay? If you have questions about, if you find points off and you don't understand why the points are off, come see me and we'll talk to you about it. Okay? Don't let it scare you. There's not many points. We're not taking many points off, but just a couple to say, hey, this was inefficient, or you didn't comment this in the right place. Okay? Questions on that? Okay, lab 1. Why didn't some of you guys provide it yet? I turned off provide, and then I went and did the grades, and like probably 10 or 20 people just never did lab 1.
Never had the lab.
Did you see Piazza where it said, do lab 1? Yes, you should always look at Piazza posts. Okay, if you didn't do lab 1, email me and beg me to turn it back on for you. Okay? And if you didn't get the Piazza post, that's even more weird because it sent an email to every one of you. Did everybody get an email about Piazza about lab 1? Yeah, if you didn't get an email, you're not looking out for your Piazza posts either. So keep that out. So lab 1, yeah, email me if you didn't do it and say, I'm sorry, I didn't know about Piazza, or whatever. Right? Okay, lab 2, that is due Sunday. Okay, at this point, lab 2 is due Sunday. And if you don't get your code working for one of these labs, I'll just take 1 out of 4 points off. The labs are not worth that much of your grade. It's like 10%, but I do want you to do an actual try to get the labs working. Okay, some people last semester just weren't getting the labs working, and then they were like leaving lab and being like, oh, I'm done. And I'd rather you at least give it a good effort to try to get it working. I guess the one that was the worst was one student. I noticed when he provided his assignment, it was like 5 minutes after lab started, and it totally didn't work. And I'm like, what, did you go in and just provide just so you get the credit for providing? And I gave him a 0. But anyway, he didn't have an excuse on that one. OK, questions on that stuff? All right. Let's see. Eclipse tip of the day was I was going to show you more debugging. You can actually see pointers. See is probably the wrong word. You can walk through a linked list while your program is running and seeing where everybody points to what. And so it's kind of cool. I would be happy to show you that if you want to stop by, and I'll show you how to do that. It's really neat. You can do something very similar in GDB itself. So it's kind of interesting to do if you want to walk through your whole list and actually see if it's properly set. Okay? All right. Speaking of sets, we'll talk about a set. OK, this one, we're going to breeze through this one because it's not that hard to understand, and I won't make you actually build sets. But sets are an abstract data type. And again, what an abstract data type is it's basically the interface for a particular type of, in this case, data type. And it basically says, hey, you've got the following functions, and those functions will allow you to do certain things. And a set is simply a list where we don't care about the order. That's all a set is. In other words, a set has a bunch of things in it. We could care less about the order, and in fact, you're not even allowed to get the order out of it. Like a set won't give you the order of your things, but it's just basically the ability to put stuff in it. Now, what you can't have in sets generally is duplicates. Okay? If you put 4 into a set, then 5 into a set, then 5 again, sets just have 2 things in them. That set has 4 and 5 in it. Okay? It's kind of similar to a math set in that sense. Okay? Because it's an abstract data type, you can build a set with a dynamic array or a linked list. Doesn't really matter. Here's some of the functions that are in a set. Okay? You've got the add function, which basically puts it into the set. Nothing weird about that. Okay? Adds an element if it isn't already present. Okay? When I say that, you should start thinking about how do I know if it's already present? Oh, I better look through the whole list. So these aren't necessarily the most efficient functions in the world, right? Then you can remove the element if it's in the list. You can also get the size of the list, and you can also query the list and say is element of, and to find out if the element is in the list, okay, or in the set. And these are going to be important because homework assignment 3 uses a set. I built it for you, so you don't have to actually go and build it. But it was like the easiest thing to build because it's just a dynamic array. Okay, you can check and see if things are in the set. Okay, you can also do some other functions. Now these ones I didn't build into your set because you don't actually need them. But just like math sets, you can do unions of a set, right? You can take 2 sets and do A union B and return what's the same in both sets, and that will give you another set, right? You could also do intersection, which replaces the set with the intersection of the other one. In other words, just the one. Sorry, did I say that backwards? Union is all of the ones from one and all the ones from the other that aren't duplicates, right? Or it doesn't duplicate it in the full list. And then intersection says you take the ones that are overlapping in both and return those to one set. Okay? You can also do subtract, which takes out the elements of one from another set and returns the difference there. Okay? So that's, those are the other functions you can do in there. Again, I'm not going to make you build these. You should just know what a set does. Because sometimes you might need to use a set. There are lots of cases where you might want to put a bunch of elements into a set and not care that there's duplicates and not care that they're in any particular order. So you should know about this abstract data type. Again, we won't be coding it, although you can certainly go and look at the code on the, in the homework assignment 3. Okay? And if you want, you could go and implement some of these other functions. They're not really that hard to implement. But let's talk about, let's see, a dynamic array set will actually add elements, just searches for the element, appends it. Right? Generally, append is because you got to search for it first. You might as well stick it at the end. Right? Remove element, searches for it, and removes it. Again, with a dynamic array, if you find an element in the middle, you better shift everything else backwards. So you've got to do that. And then is element just searches. So the asymptotic complexity for all of these things is what? I heard a bunch of people say linear. Sure it is, right? If you have to look through a set, and it's not in any particular order, you can't do binary search. You can't do any other kind of like specialized search. So it's just going to be order n. Okay? Size isn't, because size, unless it's a linked list. If you're doing size with a dynamic array, you will have the size instant because of you need to keep the size of your array. So that one's just order 1. Okay? Asymptotic complexity for a set. Not so bad. Okay? All right. Union, intersection, and subtraction are a little more interesting asymptotically. To get the union of two sets, you basically need, for every element in one set, you need to go through every other element in the other set and compare them in some fashion or another. Right? So they actually end up being n squared behavior for a list-based set. Not so great. Okay? You can create a set using some other types of data structures, like we'll talk about trees later, where you can use a set. But in this case, we're going to have to you're going to have to watch out. If you just wanted to build a union with a dynamic array, you're going to end up with asymptotic behavior of n squared. It's not so good. If you did sort the set, you'd get better, but that takes up more time to keep it sorted, and there's other issues there. Okay? So I just wanted to show you that basic stuff with sets. Okay? Boo. N squared. We don't like those if we can help it. Okay? All right. So any questions on sets? That was the whole like set thing. It's not the biggest deal. You just have to know about the functions, and you should probably be able to reason through the asymptotic complexity for those sorts of things. Questions on those? OK. So the next thing we're going to talk about are queues. At the beginning, I put a little picture of a queue, right? Queue being like a line. Anybody from a Commonwealth country in here? Like Great Britain or Canada or something else? Yeah, where are you from? Malaysia. Yeah, you know what a queue is, right? Like you probably use that in normal, like in regular speaking, right? In the US, we generally don't talk about queues as like a line that you're standing in, right? In other countries, sometimes they use queues being like, oh, we'll go stand in a queue at the supermarket, or the queue is so long to get on the T. Who closes the T, by the way? The entire T system was closed yesterday. I couldn't believe that when I woke up yesterday. I went, oh my gosh, the whole T is closed. So yeah, if you're standing in a queue, that's just like standing in a line. And how do queues work, right? If you're standing in a queue at the supermarket, the first person to get up to the register is the first person to get served. The last person to get up to the register is the last person to get served. Okay? This is a different mentality, and it's a totally different model than a stack, even though they're very similar. Queues are just first in, first out. First thing that goes into the queue is the first thing that comes out. And everybody who's lined up, they end up in order, right? When I was a kid, I got really upset about this because when I was in, let me see, it was 4th grade, and Gary Gerst, who was in my class, was decided to do a frontsies backsies with somebody else right in front of me. When you remember that from like grade school where you budge into a line and you say to somebody, you say, look, let's do frontsies backsies where I'll get in line in front of, right behind you. Like you're letting me in front of you, but then really I'm getting behind you. Except they were both in front of me and it just really upset me. And in 4th grade, you get upset about those sorts of things. Interestingly, Gary Gerst is actually, it turns out he's a great guy, as it turns out. And he's actually the principal of that high school right now. Like that's his job now. He ended up being principal. So I hope he catches the kids that budge, and I hope he remembers that, but I'm sure he won't. So look, cues happen this way. Instead of like a stack where you insert at the top, we always put it on the top. Cues, you have a front and a back, and you insert at one end, and you remove from the other end. Okay, and that's how a cue works. Okay, because you insert at one end, and then everything that's there, just like a line at the supermarket, right? Where do you go where do you get in line unless you're Gary Gerst? The back, right? You get in the back, and then you move towards the front, because at the front, those are the people that come out. Okay, that's how a cue works. All right. Cues have a few different operations that are required for the cue abstract data type. Again, it's not a data structure, it's an abstract data type. Okay, you have to be able to in-cue into a cue, right? And you insert at the end, just like in the supermarket. People always get that wrong. And where do you insert? Or where do you in-cue? Oh, at the front. No, you in-cue at the back, right? You end up going in at the back. Think of a regular old line. Okay? You can also have DQ, which deletes and generally returns from the beginning of the queue. Okay? The beginning of the list or the queue. Right? So in other words, you DQ, and the first person gets returned. The first object gets returned. And I just say object type there because it could be anything. It could be an integer, it could be a card, it could be a whatever. For the homework assignment, I believe it's just a student gets queued, in-queued, and DQ'd. Right? And then we have is empty, which just says if it's empty or not. You should, before you do a DQ, you should check if the queue is empty. Otherwise, your program is allowed to crash. Right? And that's generally true with queues. It should throw an error if you try to DQ from an empty queue. Okay? So in your case, you don't have to build that into the queue part. But know that when I test your queue, I will check if it's empty if I think it's empty. Right? You should always do those sorts of things. You can also say while not is empty and walk through the queue, right? Because you'll just keep going until it's empty. So those are 3 things that are necessary for a queue. Okay, in queue, DQ, is empty. Okay, you can also yes, question. Oh. Were you holding your hand up for her? No. Okay, 2 questions. Question 1. Go ahead, Kate. Well, depends how you do it, right? If it's an order 1 operation, I wouldn't be too concerned about it. If you're doing it with if you're setting up your queue with a dynamic array and you've got the size, I'm not too worried about it. But you don't need to, right? In fact, what you should let the person using your queue check if it's empty, right? Otherwise, you should do it. Now, if it's a linked list, yeah, that would be inefficient, right? Be inefficient. Yeah, good question. Yeah. Mm-hmm.
Let's say it's a wait list and someone is wanting to remove themselves from the wait list, but they're in the middle of the list.
This is a very good question. Yeah, this is a very good question. The only way in and out of a queue is by dequeuing until you get to the thing you want to remove. So it's much like a stack in that sense. So this homework assignment happens to be a little tricky in that I don't let you fool around with the queue operations. That's by design. Normally, you probably wouldn't use a strict queue for this sort of thing. But yeah, you have to somehow store all those other ones until you get to the one you want to remove, and then put all the other ones into like a new queue or back into the original. What's nice about a queue is, so let's say that you're at the supermarket and you're standing in line and you're about to pay. You're at the front of the queue. You're about to pay, and you realize that you forgot to get peanut butter. You got jelly and you got bread. You forgot your peanut butter, right? Okay, what you can say to the cashier sometimes is you can say, whoa, hold on, I got to go get peanut butter. And what the cashier will do is say, OK, you're going to go at the end. They could say this. They probably won't. But you can say, OK, just go to the end of the line and we'll hold your stuff here. Right? So basically, you can get in the other end of the queue and then cycle back through. Right? So that's really how you end up having to do it, cycling through. Okay? Yeah?
Why would is empty be inefficient for a linked list? Because you just have to say if there's something in it.
Oh, you're right. You're absolutely right. That when you're in a linked list, if it's empty, there won't be any. You're right. Well, no. Actually, that's a good point. If it has stuff in it, that will be inefficient.
Well, you just have to say, oh, if there's something at the front, then it's free.
Oh, I guess you're right. If there's one thing in it, you're right. We're not counting it. That's right. That's a good point. Yeah. If the head is not null or the front is not null or whatever. Yeah, that's a good point. Yeah. Yeah, that's probably not inefficient. You're right. I still wouldn't necessarily put it in your function, but you're absolutely right. Yeah.
Is it more efficient to like take a queue and then just move everything from that queue to a new queue and then delete whatever element you need to delete and then
Sure.
just copy it back over?
Is it efficient? No. Do I want you to do that? Yes. Just in this case, just to show you that that's kind of how you would have to do it. But yeah, you're absolutely right. You know, some people are a little bit clever with it, where they immediately in queue, like they dequeue immediately, put the thing at the back of the list and walk through the whole thing. That will work. You just have to be careful about stopping when knowing when to stop. You just can't use the is empty in that case. Yeah. Good point. Okay. All right. Other questions on this stuff? We're going to go through a couple more things about queue that you'll actually get to see them in action here in a little bit. Okay, so you can get the size, you can print the queue, you can get the front of the queue, you can just peek at the front, which just basically is what front does. It says what's at the front, who's at the front of the queue. You can peek at the back of the queue, etc. Okay, remember there's two ends now, whereas a stack only had one. Okay. All right, so here's what a queue looks like. Now, we're going to go through this a couple different ways, and the first time you see it, sometimes it doesn't really sink in. I know it's not that complicated, but sometimes it doesn't really sink in. Okay? Pretend this is your array, and pretend that this is the front of the queue. Okay? So where are we going to put our next value that we put in the queue? We said we in queue where? In the back, right? Okay, so the first thing that we put in was a 5. Then we put in a 2. Then we put in a 7. Then we put in a 1. Okay, and that's how the queue works. And then we're going to put in the back. Now, you should keep a current size, because that will become very important in a little bit. If you don't keep a current size, you have to do a little bit tricky math to keep everything set. It's a little more bookkeeping, kind of like linked lists in some senses, bookkeeping. But please do yourself a favor and keep current size correct. Okay, because that will help you in a few minutes. Here's how you do this. Okay, you keep two positions. You keep the front. You keep the back. The back. Some people do it a little bit differently. I like to do it this way. Keep the back at the next available spot. Okay, so the back should point or should be an index to the next available spot. These are not. I have my little pointer these days. This is like the brightest pointer I've ever seen in my life too. Stare at this one, you're going to go blind. So you keep these two positions. They are just index values. Sometimes I will slip up and call them pointers because they look like pointers. You could keep them as pointers if you wanted to. If you were doing this with a linked list, you probably could. I say just keep two index values to say what the index is to the front, what the index is to the back. And again, the back in this case is the next available space. Okay, if you're doing this with a dynamic array. For this queue, we've got 4 items in it, meaning the current size is 4. Okay, the front is this one, the back is the one after it. We're all okay on that, right? So far, so good? Okay. To enqueue an element, it's not hard. You put it where back currently points, because back the index of back, and then you increment current size and you increment back. Back ends up here, the element ends up here, current size ends up one more. Okay? So after an insertion of 8, for instance, first thing we do, or I should say during it, first thing we do is set 8 to the position in the array that back is at, and then we simply increment back and increment the current size. Okay? This is not hard. Yes? We will get to those 3 empty spaces. Let's just pretend our array starts here and this is index 0 for right now. Okay, but that's a good point. All right. In fact, you're just about walking into my next question. Yeah. So this one? Okay. We've got 4 elements in here. Okay? Index, whatever index this is, points to the front. Okay? Whatever index this is points to the next available space in the array. Okay? All we do to enqueue is we say put the value here, where back currently is, increment back so it now goes to the next one, and increment the current size. Okay? Yes?
Our back and current size always going to be the same value?
Our back and current size are always going to be the same values. You would think that. But let's hold on for a minute on that thought. Okay? Hold on to that thought for a minute. You'll see why that's probably not the case in a second. Yeah?
Why do you prefer using the array implementation over the linked list?
Why do we use the array implementation? I just think arrays are better in general. Like they're more efficient in general. I mean, I've said that before. Don't use a linked list. You can certainly use a linked list. It's just a little more. I would say it's a little more work, but not. I wouldn't. No, you can certainly do that for your queue for the homework assignment if you want. I would not take any points off for doing that. Okay. All right. So we've got this now. To dequeue. Okay. To dequeue from an element from the queue, what you do is you say what front is pointing at is the front of the queue. That's the first element, so that's going to get returned. In this case, 5 is going to get returned. Okay? Decrement current size, because we now have one fewer element in the list. Okay? And then increment the front. In other words, front is going to go from here to here. And think about a line, just a regular line at the supermarket. If this was the front of the line, guess what becomes the front of the line next? This one. Some people would say, why don't we move everybody down so the front always stays at the beginning of the list? Well, don't move things if you don't have to, right? Don't move things if you don't have to. You might think it's important to, but we'll figure out a better way than actually moving things back and forth. Remember, we want efficiency. Okay? So you could do this. You could say 5 gets returned and then move everybody else down. But that immediately becomes an order n linear operation. And we kind of want to avoid those if we can help it. Okay? There's not really much point in using a queue if we have to do all that moving. Okay? All right, and then we increment front. Now, the front is now here. Okay, current size is 4. And guess what? Do we actually put some value here? We don't. We don't bother. Okay, and let this sink in for a second. 5 is still technically in the array. It is not in our queue anymore. It's kind of like the guy just got his groceries and is kind of like still standing there, but the cashier goes to the next person. It's like if the cashier like moved the whole cash register, which would be a little weird. But that's, maybe that's, I don't know, maybe that's some other way to do it. But anyway, the 5 is a dead squirrel for our purposes. It's not used, it's not available to us in any sense of the queue. It's still in the array, but we don't care about it anymore. Don't go making it 0 or trying to make it null or whatever. If you're using a linked list, you probably would end up making it null. Different story. For an array situation, you're not going to change anything. Okay? All right, bear with me on this. Now, some problems with this. Now, we've already gotten a couple questions about what a problem with this might be. First question we got was why don't we have it start at here? Guess what? We did have it start here. I just didn't put these numbers in there. Okay, so let's say there were 6, 2, 9, whatever. Okay? Isn't it true that the way we've done this, front will keep moving up like this, back will keep moving this way as we add more elements? What's the overall problem here? Yeah. There are a bunch of things you create that you can't delete because you can't access them. Not necessarily. I like what you're thinking, but it's a little more subtle than that, actually. Yeah.
It's really memory intensive because you can't dynamically free up the space that you created until you're completely done with the array.
Yeah, well, that's a good point. Yeah, and this is probably getting to your point as well. You can't really remove these if you're still going and moving other stuff over here. You can't dynamically get rid of that. That's a very good point. Yeah. Yeah, so the back, this is kind of the one that I was really getting to. The back here, if you keep adding stuff to the queue and removing stuff, the back ends up off the end of the queue, and we end up with all these dead squirrels here, and we've only got, in this case, 6 things in our queue. And what could we do? Yeah. We could do that, and we're going to. What could we do just based on what we don't know about dynamic arrays? If you get to the end of your array and you want to add more stuff, we could create a whole new array, double the size, create a whole new array, and just keep it going in here, right? We still end up with all these dead squirrels, though. In other words, the front will keep going this way, and the back will keep going this way. And you could keep walking along, and sure, you could create a whole nother or double the size of the array, but there's a better thing to do. Okay? We could do that, but as it turns out, it's kind of bad news if you've got a queue where it just keeps growing and nobody ever comes off the front of the queue, right? I think this is the Comcast model when you're on phone with Comcast, right? Where you call up and it says, your wait time is approximately 4 hours, and whatever. I heard the other day that Comcast actually, there were some people at Comcast who were keeping people on hold until the company closed for the day and then just put them off hold. Terrible company. And sorry if anybody's family works at Comcast, but I feel for you. So the secret, dirty little secret about queues is unless something really bad is going on, right? Another example is if it's before a snowstorm and you're at the supermarket, the lines keep getting bigger and they'd never have enough staff. But in general, hopefully, the number of people coming into the queue is roughly the same as the number of people leaving the queue. Okay? It might grow and it might shrink, but it's roughly the same, and you hope so. Right? If you're a supermarket, you hope that there's always some people in line, so you're selling stuff, but you don't want the lines to be more than 3 or 4 people. Okay? So generally, your queue isn't going to grow super big, and it's not going to shrink down to 0, but it will go up and down a little bit. Okay? What's nice about that is we should just reuse all of these elements. The solution, as was brought up a few minutes ago, is to say, fine, if back gets over here, just move the back to one of these, the front, and if it's a dead squirrel situation, who cares? This is all wasted space right now, right? Actually, all of this is wasted space in the sense that we're not using it. They're all dead squirrels, right? So we might as well put the back here, and this is called a circular queue. Okay? Circular queues are great because let's say that you had at maximum 5 people in your queue. This would work fine. It would work all day and nobody'd ever have trouble with it. Okay? The first time I ever saw a queue, I won't tell you when because it's going to date me. First time I ever saw a queue in programming languages was on the original, now I just dated myself, IBM PC, right? Which came out the early 80s. And I was learning how to program on it, and there's a keyboard buffer. When you type on your keyboard, right? When you actually type on your keyboard, right? The computer needs to store that character that you type while it's doing something else, and it will eventually get around to handling that keyboard thing, right? Something handles it immediately. What happens is the keystrokes go into a queue, and it happens to be a circular queue because they figured nobody could type fast enough so that the queue, which was only 128 characters or something, such that the queue could actually, nobody could type 128 characters faster than the computer could actually get to it, right? Now, of course, that's not true if your program's in the process of crashing or doing something else. But the point is that that's not a bad model. Just have this thing go around. And there was no way to make it bigger or smaller. They just had it, whatever. It would just stop accepting keyboard input if the queue was full. Right? But it was exactly that, okay? And so we have this situation very often where things will be consumed out of the queue as more or less as often as they're put in. And we can use this cool circular queue size to do this. Okay? Notice something here. If the front is here and the back is here and this is a dead squirrel, right? It doesn't actually matter, but there's only 2 things in this whole queue right now, the 4 and the 3. Okay? We have to keep track of that. I'll show you how in a couple minutes. It's not that hard, but I'll show you how in a couple minutes. But you have to keep track of that. Okay? All right, here's an example of how this circular queue works. Okay? What I'm going to do here is I'm going to have the initial, the step 1 here, step 2 here, and then I'm just going to shift them up. So then this step is going to come up here so you can see both steps at the same time. Okay? You'll see how it works in a second. All right. Let's say that we start with a queue that we've already done a bunch of things. Maybe these are dead squirrels, or they're definitely dead squirrels. Maybe there's stuff in there. But let's say we start out in this state. The 8 is here, there's the front. The back is here. Okay? When we in-queue, remember how we in-queue into a queue. We put the next thing at the back, and then we increment the back. Okay? In this case, we're going to put the element here, so we're going to in-queue 1. We're going to put the 1 here, and then we're going to increment the back, but it's going to be bigger than what? The array capacity. It's bigger than the array capacity. So if, you can do this a couple different ways. We'll talk about both of them. You can do this a couple different ways. If you increment back, and it's greater than the capacity, what does back become? 0. Okay? There's a sneaky math way to do that. It's not sneaky, it's just a math way to do it, right? You can say, so you could say back equals back plus 1, right? And then you could say if back is greater than the capacity, right? Then we're going to say back gets 0. Okay, you could do that. That's one way to do it. Okay? Anybody, well, I know some people have already done part of the assignment where you've thought of this. But there is a way to do this without doing an if statement. Okay? Somebody who hasn't done the assignment yet, you'll have to be honest. Think about this. Yes?
I think that if you do back and their array size, you'll step back from it, if it's more than array size minus 1 maybe, and then you use 0 to over the array size.
I like what you're thinking. I know you did this in Comp 11. You used the modulus operator, which is the remainder operator. It's exactly right. Let's think about what it's going to be. Back gets what? Can you think about what this using the modulus here to figure out what it actually gets? Modulus gives you the remainder. What is, let's see, what is 10 modulus 10? 0, because there's no remainder. What is 10 modulus 11? 10 modulus 11 is what? 10 modulus 11. Oh, that was a bad example. Let's do 11 modulus 10 first. 11 modulus 10, right? 11 mod 10 equals 1. Because you divide by 10, and then the remainder is just 1 left over. Okay, if we did it the other way around, I'll do this. 4 modulus 10 gives you what? Yeah, be careful. 4 modulus 10 says 4 divided by 10, which is what? 0 with how much remainder? 4. So 4 modulus 10 gives you 4. Okay? So, you ready for this? Back gets what? Somebody who thinks they can get it, even if you've done the assignment. Yeah?
In parentheses, back plus 1, flow current, mod array size.
Back plus 1 modulus. Let's use capacity, right? Just because we normally call it as capacity. Okay? Will this work? Let's think it through. If back was 0 and we were moving it to 1, we want it to stay at 1, right? So one modulus or remainder capacity, which is 10. We already said 4 modulus 10 gives you 4, so 1 modulus 10 gives you 1. That would be right. All the way up to the capacity. If we're at 10, if we are at the capacity, let's say the capacity was 10, right? And back was at 10, right? 10 plus, actually, let's make it 9, because our indexes always start at 0. If it was 9, 9 plus 1 modulus 10 gives you what? 10 modulus 10 gives you 0. It wraps right back around. Okay? So you can do this instead of doing the if statement if you want to. Okay? That will definitely work for wrapping this index back around. Okay? If none of that made sense to you, that's OK. You can still do it with the if statement, or you can come see me and we'll talk about it. So this is what's happening after in Q1. You've put the 1 here. You've incremented back using our fancy back plus 1 mod capacity, and it ends up here. And the current size is now 3. Be very careful to keep the current size updated. Okay? All right. after in Q3, so we enqueue another 3. This was the one we just did. And then we enqueue 3. We enqueue 3, back was here, so we put the 3 there. We increment back, current size is 4. So far, so good? Okay. Let's dequeue some things. Okay, let's dequeue 2 things. We start with this one, and we dequeue 8. That means 8 gets returned, and we increment front, and then front is here. And then we dequeue again. We return 4, and we increment front, and front ends up here. So this is what we're left with. Front is here, and back is here, and how many things are in the queue? 2 things are in the queue in this section here. This one and this one. Okay? You've kept it updated because you're paying attention, right? You got to keep it updated. Questions on that? Okay, if we do a dequeue one more time, right? I believe that's what I'm doing next. Let me peek. Yep, another dequeue. So we're here, and we dequeue the 1. Okay, we return the 1, and then we do front gets what? Front plus 1 mod capacity. Okay, and that bumps the front over to here, and there's 1 thing left in the queue. Okay, and now we're like this. Now, this, by the way, looks maybe like what you started with, or something like that, right? If you started with an empty queue, and you put a 3 in it, back would have moved here, front would have moved, front would have been there, and we're good to go. So it just circles around like it's supposed to do. Okay, all these dead squirrels. Okay, all right. After a final dequeue, then we dequeue one more time. We've got the queue here, dequeue here, and 3 ends up getting returned to us, and we increment front, and we end up with back and front being the same. Okay, and how many things are in the queue? 0. Okay. Now, you do have to be a little bit careful with the front and back being the same, because if front and back are the same, if you're not careful with it, you can end up with either a full queue or an empty queue, and you won't necessarily be able to tell the difference. So you have to keep track of it. There are sneaky ways to do that, but that's that. Okay. Question.
When you initialize a queue, should the front and back both be the same thing, or should one be like, they should be the same, right?
It should be the same, yeah. Think about it, because what do you do right now? If we enqueued again, we would put the value here and then move back to here. Front points to the one that's the front, and back points to the next available one. Yep. In this case, if front equals back, then if front is the same as back, this leads to a condition where there's either nothing in the queue or it's full, but we'll get to that in a second. Okay? All right. So you have to carefully rely on current size. All right? You could say that current size is the following. Back minus front plus the capacity, mod the capacity. Let's see if it works for this one. How many things are in this queue? 1, 2, 3, 4, and the back is the next one. So there's 4 things in the queue. If this was index 1 for back, 1 minus the front, which is 7, gives you -6. The capacity of this is 10, because it goes 0 to 9, that's 10. So -6 plus 10 gives you 4. 4 mod 10 gives you 4, which is indeed the current size. 1, 2, 3, 4. So you can play interesting tricks by not keeping current size. You can do it. Just be a little bit careful with that. Okay, just be a little bit careful with that. Okay. Any questions so far? Okay. Look what happens when you reach the capacity. Okay? When you reach the capacity, all right, what would happen is that your current size is too big, and we need to expand. You will practice this in the lab on Monday. Okay, next week's lab is on expanding a queue, and it's a little bit tricky. Okay, it's a little bit tricky. Let's actually try it for this one. Okay, sometimes you have to expand. When you do end up with a full queue, you'll have to do it. This circular queue works only until you get to a full queue. Okay? All right. Let's think about what we're going to do to actually expand this. Okay? Current size is 10. All right? If we tried to expand one more time, or if we tried to add one more to this. Okay, we couldn't because it's full. Like that is no longer a dead squirrel, right? That is the next available spot, but it's also the front. Okay, so either we got here by dequeuing until that's the case, or we got here by inqueuing until there's 10 elements. Okay, what do we do when we expand a dynamic array? What's the first thing that we do? Create a new array that's how big? Twice the size. Okay, so I'll create a new array here for this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I believe that's right. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, 19. I went too many. Did I count right? There we go. OK, so now it's double the size, correct? OK, and it should hold 20 elements now. With a dynamic array, you normally copy all these guys down to the front, right? Will that work in this case? Why wouldn't it work? What do you think? Why wouldn't it work?
Because the 3 isn't actually the first element in the list in the middle.
This is not the front of the list, right? This is the front, this is the back. If you tried to copy everybody over, right, then you end up with the front and the back still pointing at each other and at the same element, and you haven't gained anything for yourself, right? There's no way to like continue it without, because then the 4 and the 1 would be still there, and you'd still be overwriting things. Okay? What's a better way to do this? Yeah.
Copy by just dequeuing.
You could do that. You could copy by dequeuing. You could dequeue 8, and then what would you do with it?
You move it to 0.
Yeah, you'd move 8 here, and then 4 here, and then 1 here. So you could do it that way, right? Dequeuing is fine. That's a little more overhead than we necessarily want to do, but we could do it that way, sure. Yeah, you had somebody else had their hand up over here. Who was it back? No? OK. Yeah, you did. Is that what you're going to say? OK, you're going to say the same thing. Somebody else who has a different idea. Yeah. Yeah.
Sorry. Can you just copy them one to one and just keep the same front and back? So 3, 7, 5, new array.
If you keep the same front and back, the problem is you're still going to have a 4 here. And how do you actually, like, it's still going to be the same problem, right? So you still want to, the real idea is end up with your 8 here so that our front ends up here and our back ends up where? Yeah, at the 1 plus the capacity back there, or the end of the amount before there, right? The next available spot, right? So really, you could do the dequeuing thing, right? Or we could just write a for loop to do it, right? We could write a for loop that says, OK, we're going to start at I equals 0. Let's write the for loop. Might as well, right? For int I equals 0. OK. Now, what's I going to go up to? How many elements are we going to copy out of here? Yeah? Current size or capacity, either one. Our initial capacity. OK. Less than capacity, I'll call it. OK. I plus plus. OK. And then we need to actually do the copying itself, right? So let's say we have our original Q. We'll just call Q, right? And let's say we'll have Q2, which is sorry, the original one. That one's Q. This is Q2. Q is the one on the board, or the one on the overhead, right? So let's do that, and we'll call this one. We'll call this one Q2. Okay? We need to copy from 8 needs to go into the first position 0. Okay? So let me start this one out. Q2 location something, right, gets Q location something. What are those two things going to be? Do this. Talk to your neighbor about it and fill those in. Okay? Okay, who thinks they've got it? A couple people do. Daria, what do you think? Yeah. Q2I, okay. Front plus I, and then what? Sorry? Modulus, yep. Capacity. And we're still talking about the original capacity. Does this work? Let's see for a couple of these if it works. In this case, we've already got the array here. So I like this, Q2I. In other words, we're going to start from 0. Right? And as Q goes up, we're just going to go boom, boom, boom. I like that because it's nice and simple. All right? So, OK. I right now is at 0. I shouldn't point it there because it's not a pointer. I'll just say I is 0. OK. So front plus 0 mod the capacity. In this case, the capacity is 10. So 8 mod 10 we said was 8, because 8 divided by 10 gives you 0 with a remainder of 8. OK? So at, was that right, though? Sorry, it's not, why did I say 8? I meant 7. It's the index value, not the value here. 7 mod 10, remainder 7 gives you 7. Or 7 mod 10 gives you 7. So the 8 goes here. OK. Now I is 1. OK, and then we've got, it's going to go into position 1, and it's going to go from 8 mod 10, which is 8. So it's going to go there. So the 4 comes in there. All right, same thing for the next one. Nothing's really changed. We're going to get 9 here. I'm sorry. I should have done it with A's and B's and C's or something. 1 goes there. OK, now, at the next one, when I is now 0, 1, 2, when I is now 3, let's see what happens. OK, so we've got Q2 at position 3, that's this one, which is where we want, gets Q2 of the front, which is 7, plus I, which is now 3, is 10, mod 10. 10 mod 10 is 0, which means we're going to grab this 3, and guess what? 3 goes there. Now, does you see how that works? In the end, it's going to be 3, and then 7, 5, 8, 2, 6, 9. OK? Where are we going to set our front to the new Q? Front gets 0. Where are we going to set the back to? Back gets the old capacity. And we're ready to go, because the next available spot is this one. And now we've got a good Q. OK? Yes?
When we were talking about it, we just said to update front afterwards.
Sure, you could do that. You could update front afterwards. You could basically say QI gets what?
Front, and then you update front,
Front, and then you'd have front plus plus. And then how do you make sure the wrap around?
I mean, the same way that we kept it.
So you could do front gets front plus capacity mod, or front plus 1 mod capacity. Or you could do front plus plus if front is greater than capacity. You could, or equals greater than or equal to capacity. You could do that. Yep.
There's a difference in terms of like efficiency and how quickly.
This is about as efficient as you're going to get, right? This is about as efficient as you're going to get. This is maybe a little less readable, which is not a good thing. But you might just, you could put a little comment here saying, retrieves from the front, increment, and makes sure the front wraps around the circular Q or something like that. But no, they both are the same. They would work the same, more or less. There might be a little more efficiency here, just because you're not doing an if statement, and you're not doing the, you don't have to update front, right? We're only updating I. OK, good. Other questions on this? OK, so that's how we do Qs. OK, where else do we see Qs in the world? Well, we see Qs lots of different places. Submitting jobs to a printer go into a queue. Although, much like some of the question about the class list, deleting from a queue, it's probably not a strict queue, because you can generally delete from a printer queue. If your job is in the middle of a bunch of jobs, you can say, I want to delete that one. So it's not a real queue in that sense, that it can't remove from the center. Ticket counters, supermarkets, anywhere you stand in a line, right? File servers. If you ask for a file and somebody else asks for the file, if you ask for it first, you'll get it first. That's the way it goes. First come, first serve. Anytime you have first come, first served. Call centers, we talked about that. And then my own research actually involved queues. As it turns out, so my research was on, you know how you have CPUs, I think I told you the first day. You have CPUs in your computer and you have GPUs in your computer, a graphics processor, right? Well, it turns out both things can do work, and then people have made them so that they can both do like regular programs, even though it's a GPU. My work involved trying to make sure that both could work together efficiently. And this is literally a slide from my PhD dissertation that said, applications are moved from a main queue into a device sub-queue based on a set of rules. And all these rules are how things actually go from one thing to the next. And so you actually, for my research, I used queues all the time, right? So I got very familiar with how these work. Okay? So you see things like that. All right? Real life has lots of examples of queues, much like real life has many examples of stacks as well. Okay? Questions on queues in general? If you have trouble with this, go back and look at the slides or come to office hours. Yeah?
Just like a general question, C++.
Mm-hmm.
Would you ever need to create a queue, or could you just use like an array, which would be like more useful?
Well, yeah, would you ever need to use a queue? So again, remember, the reason we have these abstract data types is to make it easier on the person using the structure, right? So if you have a problem that you need to use a queue for, yes, somebody probably used an array to build it, but it's easier for you to like think about, oh, I only have to have it do this. Oh, am I going to insert at the front, or am I going to insert at the back? Or you know, I mean, for a list, if it was just an array, you'd have to keep all this stuff, track of all this stuff. The other great thing is if you have a circular queue, right? The nice thing is it's all handled for you. Like all of the expanding is handled, all of the circular business. You're being most efficient doing that. So you probably want to create a queue if you're going to use one. The C++ standard library has a queue built in. You'll use that in a couple of labs where you'll see that. Okay, but yeah, in general, you'll use this under the covers, but it abstracts away a lot of the details using the queue. In-queue, D-queue is empty. That's all you need to worry about. Okay? All right. We actually didn't talk about asymptotic complexity. What's the asymptotic complexity of adding to in queuing? Constant. Woohoo! What's the asymptotic complexity of removing from a queue? Constant, right? Because you just need to return it and increment a pointer. That's not going through all of them, right? Two great things about a queue are their constant behavior. The only non-constant behavior is when you actually have to expand, and that happens rarely. So that's a bonus on that sense. Okay? All right. Homework 3. If you haven't looked at it yet, please start it soon. Right? In other words, yesterday. Homework 3 is on class waitlists. So when you signed up for this class, if you are not a major, you would have been put into a waitlist for the class. Like I don't even think the class allowed non-majors to actually enroll until we figured out the waitlist. And then it turns out I just let everybody in. Because what I do is I increase the capacity of the class so that everybody could get in. Right? This homework assignment just models this. Okay? And it models it in the sense that it basically is you have a class roster which you are allowed to go on to if you're a major. Okay, so no matter what, as long as the class capacity hasn't been met, if you're a major, you get to go on the class roster. If you're not a major, you go into a wait list and what's called an other wait list, which basically means that you're in a wait list waiting to get in the actual class. Okay? If the class is at full and you're a major, you still go on a wait list, but you have to go on a different wait list because you're a major and you should get preference. Okay, so there's two wait lists and there's an actual roster. Here's how we model this. The roster is a set, okay, because the roster doesn't have any order necessarily to it. Okay, and we could order you by last names or something like, or what year you are, or whatever, but who cares? Once you're in the class, you're in the class. Like I don't care what order there is in the class. Wait lists, on the other hand, generally have an order. First person on the wait list is generally the first person who gets into the class. Okay, so that's what this model is all about. Okay, you'll have to look through the details look through the actual class about these things called enrolled and major wait lists. It's basically the way we figure out whether or not you're on which wait list you're actually on. Okay, you'll see. A couple other things about it. Let's see, did I put this on here? Yeah, the isiscourse.h file has a lot of information in it about how this process works. It's a little bit, we had to be very explicit about how the process works. Okay? When the class enrollment is increased or a student drops, simplification, people can come off the wait list until they get up to the enrollment. Okay? In other words, if the wait list, if you are in the class and it's full, and then I say, oh, or somebody says, oh, increase the capacity, people come off the wait lists in this order. The major wait list, then the other wait list. Right? And that's that. Yeah?
You exhaust the major wait list before going to the other one.
You exhaust the major wait list before going to the other wait list. Yes, if you can. Right? If you increase the capacity such that everybody on the major wait list gets off, then other people from the other wait list can get in the class. Okay? It's a sign, definitely a simplification. Yeah?
There isn't a limit on the major wait list. So there could be that
There are no limits on any of the wait lists. Right, right. So there can be 1 million people on the wait list, but only 2 people in the class. You know, that'd be an interesting class. Popular one, I suppose. If President Obama was teaching a class and only 2 people in it, 1 million people would sign up, right? I mean, maybe. You never know. Everybody in school. I don't know. OK, so you can't break the queue interface. Now, this leads to some consternation in the sense that if you're trying to figure out, and we had this question earlier, if you're trying to figure out if 5 is in the queue, if student 5, whatever, is in the queue, you can't look through the queue and say, yep, 5's in there, and leave the queue alone. You have to do something sneaky, which generally involves DQ, 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 yep, there's there, DQ, 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 and then in queue, in queue, in queue, onto the same queue. Okay? Part of the reason I'm doing this is to make sure that we have the ability to test your queue, like if it can expand, if it's circular, et cetera, et cetera. So that's part of the reason we're doing that. The other part is to show you kind of how sometimes you're limited by the data structure or the abstract data type that you choose. Okay? A couple people have already asked me about this. Can I just take a queue and in-queue into another queue? You certainly can. What you can't do is if you have 2 queues, you cannot say Q1 equals Q2. Right? There's a problem with this. Because of the way dynamic arrays work, this will actually break in one of 2 ways. It could break in the sense that this queue, these 2 queues are really the same queue. In other words, under the covers, they both point to the same object. And it breaks in a second way, where when you try to delete one queue, you accidentally delete the other queue, right? And then you're in trouble. There is a way to get around this. Okay, there is a way to get around this. It's called building this thing called either a copy constructor or building what's called an operator overload for the equals sign. Okay, I'll write it like this. Operator equals overload. Oops, overload. What that means is when the compiler sees equals between these 2, it goes into a function you've created and says, this function knows how to make that copy happen correctly. So you don't need to do that for this assignment. If you want to make this work, I'm happy to show you how to do the copy constructor. Next week in class, we'll actually get to how copy constructors and operator overloads work. But it's a little more advanced than what you need for this assignment. I'll go into it. I'll show you how to do it. But just don't try to create 2 queues and then set them equal to each other, because you will wreak havoc on your program. Okay? You'll lose queues. Other queues will be like you'll end up with double freeze and all this stuff that you don't want to deal with. Okay? All right. Questions on the assignment, homework 3? Yes?
Can you say a few words about enums?
Yeah. So that's a good question. So there's these things called an enum, which, let me pull it up. Let me just show you what it looks like. It's for those of you who haven't looked at the code yet. Let's see. How am I going to do this? There, sets and queues. Let's see. I believe enums are in the isiscourse.h. Notice, as I said, isiscourse.h has lots of information about it in there. Okay. So here's what the enum is in this case. So we've created this thing called an enum, which stands for enumeration. Okay, and all it says is there's a type which is called an enrollment status. It's a type that you're creating, a new type, and it's made up of 4 things: the name none, the name enrolled, the name major waitlist, and the name other waitlist. And what that means is, under the covers, these are just integers. This one's 0, this one's 1, this one's 2, this one's 3. But you can refer to the enrollment status by this name, right? And it makes it so that you don't have to remember that, oh, major waitlist is the number 1 or 2. I even forgot, right? Right? Major waitlist happens to be 2. You don't have to put equals equals 2 anywhere. You can say equals equals major waitlist, and that will allow you to use names instead of numbers. It's strictly for humans to understand. Like, it makes it easier for humans to understand it, right? And you can have things, because it's a type, you can return it as a type. Like, for instance, right here, the enroll student function takes a student and then returns an enrollment status, right? And the enrollment status is either the student is not in the class, either the student is enrolled in the class, or the student is on the major waitlist, or the student is on the other waitlist, right? And that's what it returns, which is kind of cool. Okay, you can actually do that. Now, if you're in another function and you want to refer to this, because it's in the ISIS course class, you have to refer to it as ISIS course : enrollment status. So it gets a little bit. But if you look at the main.cpp file, you'll see that on there. Okay, does that answer your question about enums? They're just another way to make it easier for humans to understand when you have a list of numbers or something. Okay. Other questions on this assignment? No? Yes?
In your expand function, won't you have to set the new array that you created that's expanded? Don't you just set that equal to your original waitlist array or whatever?
When you the array, you can set an array just like you would do for because under the covers in the Q class, you can set things as much as you want,
So you could set
right?
you can set two arrays equal.
You can set 2 arrays equal to each other because we know that works fine,
Yeah.
right? But outside the Q class, you can't go and in the ISIS course thing make another function in Q that does this fancy stuff where it checks for enrollment. You're not allowed to do that. Okay. All right. Other questions on this? I beg you to please start it now if you haven't yet. Those of you who have, awesome. Other questions on this? Okay. Unfortunately, we didn't get to recursion. We'll start that on next week. Monday technically is a holiday. So another Monday we won't do it. Wednesday we do have class as normal, barring any more acts of God. And then Thursday we also have class. So 2 days next week, but it's Wednesday, Thursday, not Monday, Wednesday. Okay, your Thursday classes are not happening next week. Okay.